Hello, I am Dr. Michael Grieves, and welcome to the SIGGRAPH 2026 Frontier Workshop, Digital Twins for Science and Industry. For some time now, I have been referring to digital twins as a third millennium development. When I introduced the concept in 2002, the year after the third millennium began, the industries of application were just automotive and aerospace. Since then, the scale and scope of digital twins has exploded. Digital twins are involved in all types of manufacturing and industrial engineering, healthcare and life sciences, construction and civil engineering, smart cities and urban planning, shipbuilding and ports, and even agriculture and food systems. There isn't an industry or even activity that isn't exploring the use of digital twins to make them more effective and efficient. We have even moved into non-tangible uses such as supply chains and manufacturing processes. On the science side, a great deal of inquiry and experimentation is being done with digital twins. I might mention, for example, the new nuclear reactors are not feasible without digital twins. There are new and exciting opportunities on the horizon for digital twins. The two I'll mention briefly are digital twin front-running simulation and agentic AI. Front-running simulation seeks to act as a crystal ball in the future by continually taking the present state of reality and running ahead of reality by predicting future states and actions that we need to take to make those future states meet our goals. Unlike traditional approaches that primarily react to events after they happen, FRS seeks to always stay ahead of reality by maintaining a continually updated understanding of the present and projecting that understanding into the near future. By combining real-time data, models of reality, simulation, and computing capabilities, FRS evaluates multiple possible futures and estimates the probability of outcomes that could affect the achievement of operational goals. The purpose of FRS is not simply to detect anomalies or predict failures, although that's highly useful, but to support navigation toward desired operational goals while minimizing the consumption of scarce physical resources. When simulations indicate an increased probability of an undesirable future state, such as a bottleneck, equipment failure, schedule disruption, or quality issue, FRS can evaluate alternative actions and determine which intervention offers the highest likelihood of success. In this way, FRS extends the traditional digital twin activities of replication and prediction into navigation, enabling organizations to move from reactive management and physical trial and error toward proactive, information-driven decision-making that continuously improves operational performance. Agentic AI has the potential to becoming a foundational capability within digital twins by extending digital twins from passive representations of reality into active participants in goal-directed operations. Traditional digital twins up to now primarily replicate and predict the state of physical systems. Agentic AI adds the capability to reason, plan, coordinate, and act on behalf of those digital twins. In this role, an AI agent can continually evaluate the replicated state of a system, simulate alternate future conditions, and assess risks and opportunities, and recommend or execute actions that improve the probability of achieving our desired goals while minimizing the consumption of scarce physical resources. An equally important role for agentic AI is as an interoperability agent within a digital twin metaverse. In large enterprises and ecosystems, digital twins are often developed independently using different data models, ontologies, communication standards, and simulation approaches. These differences create barriers to collaboration among digital twins. Rather than requiring every digital twin to conform to a single universal standard, which I think is probably impossible, Agentic AI can function as an intelligent translator and moderator. The agent can understand the semantics of multiple digital twins, map concepts between them, resolve inconsistencies, and dynamically translate and map data and information from one representation to another. This allows digital twins representing manufacturing systems, supply chains, transportation networks, energy systems, and other domains to exchange meaningful information and coordinate their action despite differences in their underlying architecture. Thank you for listening, and I trust you'll enjoy the rest of your workshop.